Hi all, myself Misna Manaf, a final year BTech student of Electronics and Biomedical Engineering Department from Adishankara Institute of Engineering and Technology. So I'm here with my seminar presentation which was on the topic Dual Control Modes in Rehabilitation, Pressure and Muscle Signals, which was guided by Dr. Remya George, Professor and Head of Department of Electronics and Biomedical Engineering. So these are the contents of the session. First of all, we'll be going through the abstract, followed by introduction, literature survey, objectives of seminar, overview of rehabilitation, single control and dual control modes, major biosignals used in rehabilitation, and mainly we'll be focusing on major two signals, which is pressure signals and muscle signals, their applications, current challenges of dual control modes in rehabilitations, future scope, and finally coming to the conclusion and references. Rehabilitation engineering is rapidly evolving, and the integration of biosignals into the control system has opened new possibilities for patient-centered therapists. So, in this seminar, I will explain how the biosignals, mainly pressure and muscle signals, have shown great promises in developing adaptive and user-centered rehabilitation devices. We'll also examine various sensors and electrodes used for acquisition of muscle and pressure signals. So basically, when it comes to the introduction of rehabilitation, as we all know that it aims to restore the lost function and improve quality of life after injury or any certain type of illness. And traditional rehabilitation often rely on single input like EMG or pressure, which may not be efficient for patients with limited control. So to address this, dual control mode system that combine pressure and muscle signals offer a more adaptive and responsive approach. So these systems support patients through various recovery stages by enhancing accuracy and user management. This seminar explains how integrating these two signals can improve rehabilitation outcomes and device performance. So this is an overview of rehabilitation. It shows how rehabilitation facilitates adaptation to health condition. So when a patient falls ill with persistent problems from a health condition, they fail to sustain personal equilibrium in day-to-day life. So this is the time when they approach a rehabilitation specialist or a therapist. So what they basically does is this therapist provides a rehabilitation plan and advise the patient to do so. So after doing this rehabilitation plan with needing actions to assess the adaptation, patient achieves a personal equilibrium sustained without falling ill, managing typical fluctuations and changing. So as you can see, traditional rehabilitation always requires a physical support from a therapist. So traditional rehabilitation is relied on manual therapies and physical exercises which is supervised by therapists. However, with the advancement of biomedical engineering, the field of rehabilitation engineering has emerged, focusing on the development of technology driven, patient centered solutions that support and enhance the rehabilitation process. So, this is basically a single mode type of rehabilitation. So, as I said, single control modes, it only uses a single type of biosignal or sensor input to operate your rehabilitation devices. It can be of any type like EMG only control, pressure only control, or IME only control. In EMG only control, we will have a device which is driven purely by muscle activation signals. And for pressure, the device responds only to foot insoles or grip bulbs or force pads. And the third one is IMU only control, which has a motion or an angle of limb, which directly drives the system. So this figure depicts a finger by finger exoskeleton robot which has 6 degrees of freedom for the fingers. So the first degree of freedom is linear displacement. The second degree of freedom is abduction for the fingers. And the third and fourth degree of freedom is rotational stages for flexion and extension for distal and proximal phalanges. So proximal phalanges is located at the joint which is between the finger and the palm, and the distal phalanges comes at the fingertip. And the fifth and sixth degree of motion is for proximal and middle phalanges, so they can flex together rather than mimicking independently. So here we have a labeled picture, which is numbered like 1 2 3 and so on. So the first one is DC motor, which drives the exoskeleton motion, and the second one is worm screw, which helps to transmit rotatory motion from the motor. Third one is straight gear, converts worm screw motion to finger joint actuation. Fourth one is encoder gear for position measurement. Fifth one is encoder which measures joint angles to track finger motion. Sixth one is finger link interface where the exoskeleton attaches to the phalanges. The seventh one is gearbox which provides a torque transmission. Eighth one is additional gear train which is a part of mechanical reduction for smooth motion. And ninth one is joint link which aligns the exoskeleton with the user's finger joint. And 10th one is a hand base holder which is basically for supporting the hand. And the last one is sensor housing which measures the interaction pressing force between device and finger. The second single mode rehabilitation device is a table top up in effective robot which is helping two basic movements which is hand opening and closing, basically grasp gestures. So it basically has two motors M1 and M2. This helps to drive a belt driven linear carriage that changes the finger spacing. And the second one is for a rotation stage transmitted through parallelogram carriage and internal rods, so the user manipulates a knob with consistent finger orientation. So these are some of the significances and applications of single control mode rehabilitation. So significance are foundation for dual and multimodal systems. So as I said before, from single mode devices, single mode rehabilitation controls forms a basis or a foundation for dual and multimodal systems. And it also helps in signal specificity because it is only dealing with a single type of signal, and then it also helps in clinical acceptances. And when it comes to the applications, EMG only control applications include controlling prosthetic hands using forearm EMG and also triggering functional electrical stimulations FES in stroke rehab. And for pressure only control applications include foot pressure insoles for gait phase detection in exoskeleton and hand rehabilitation for strength training. And IMU only control applications include motion-based rehab games and exoskeletons where joint angle directly maps to device motion. So now we move on to the main point of the presentation, which is dual control modes. So dual control in rehabilitation refers to the use of two complementary input signals to control assistive devices, exoskeletons, prosthetics or rehabilitation games. So unlike single control which only uses EMG or only pressure signals, in dual control mode they fuses two sources of information. For example, they'll be using EMG plus pressure or IMU plus pressure or EMG plus kinematics. So this combination improves both responsiveness and accuracy, which are critical in rehabilitation where patients often have weak or inconsistent signals. So why this dual control is basically needed in rehabilitation technology? So in single only EMG, early intent, but it was noisy and fatigue over time. So when it comes to single pressure only, it was stable but reacts after motion or force occurs, which was also slower. And when it comes to dual control mode, it merges the strength, fast like EMG and stable like pressure. So first of all, we have pressure signals. So pressure signals are measurements that represents the force applied over a surface area captured by sensors when an object or body part presses against them. In rehabilitation, pressure signals are commonly used to detect physical interactions such as gripping, stepping or squeezing. So you can see our basic pressure signals. It is an illustration of pressure signal from pressure pulse. So it shows how pressure pulse interact with an interface under different stress conditions. So it shows the signals, shape and behavior depends upon the nature of the stress at the interface. So next we have several type of pressure sensors which are used for the acquisition of pressure signals. So the first one is piezoelectric sensor, then we have piezoresistive sensor, then it comes capacitive sensors, and finally we have dielectric sensor. So in this session I'll be focusing mainly on piezoresistive sensors as they are mainly used for many applications in rehabilitation. It is developed to measure strain, pressure or touch via resistive changes. So first of all, we'll go to the working of what is piezoelectric sensor. So piezoelectric sensor basically works under the principle of piezoelectric effect. So that is when mechanically deformed, the crystal generates a certain voltage. And when force is applied, the dipole inside the material realign and creates a surface charges. So this surface charges can be converted into force. And the major disadvantage of piezoelectric sensors are they are not able to measure static forces well, which leads to the development of piezoresistive sensor. Okay, so piezoresistive sensors, so the basic principle behind it is the resistance changes under applied stress. It is made up of several conductive polymers, and you can see some tangled lines in piezoresistive sensor. They are doped silicon between the two materials. So when no force is applied, the materials inside are loosely packed, loosely connected, and when a force is applied on them, the distance between the particle changes. So the contact area increases, which leads to the decrease of resistance. And the disadvantage of piezoresistive sensors where they have drift with temperatures, and they are limited sensitivity at very small forces, which led to the development of capacitive sensors. So next comes the capacitive sensor. Here the capacitance changes due to the change in plate distance. We have two dielectric material which is separated by, we have two conductive plates which is separated by a dielectric, and when a force is applied in the dielectric, it get compressed, so the distance between them is reduced, and hence the capacitance increases. And the major disadvantages of the capacitive sensor was they were sensitive to humidity, and this leads to the development of diboelectric sensors. So next one is triboelectric sensor. It works under two basic principles, which is contact electrification and electrostatic induction. So when two different dielectric layers are placed together, when a force is applied, the electron transfer between the surfaces takes place, and this is called diboelectric effect. And on separation, an electric potential is formed between the electrodes, which generates a current flow. So small disadvantage is that not in all cases, but some shows drift due to environmental conditions like humidity and surface roughness. So these are the four sensors which are used for the acquisition of pressure signals. So we'll be, as I said before, we'll be focusing on piezoresistive sensor. So this is a working principle I've already mentioned. When a mechanical stress is applied, the following changes happens. The internal structure of the sensor material changes, leading to a change in resistance. And this resistance change is measured by a readout circuit and translated into pressure or force data. This I've said before. So this is the equation which shows change in resistance is equal to initial resistance into gauge factor and strain due to applied pressure. So pressure is then related to resistance change, that is P is directly proportional to delta R by R0, which is initial resistance. So this is a basic construction of piezoresistive sensor. It has several parts. The first one is silicon diaphragm. It senses the pressure change. Next one is the silicon diffused strain gauge. It converts the applied strain into proportional electrical charges. Next one is metallization. It provides electrical connections. Next one is silicon to glass anodic bond. It connects the silicon to the glass chip. Next one is the die attach material. It helps for attaching the entire assembly. Next one is a through hole for backside pressure inlet. It helps the pressure to get inside through the backside. And next one is a bond wire, which helps for the connection to the external atmosphere. Next one is a silicon sensor chip. It is for sensing the pressure. Next one is a glass carrier chips. It provides attachment to the sensor housing, and finally sensor housing is for the protection of the chip. So this is a mechanism representative type, and corresponding install system or PSD sensors composed of piezoelectric and piezoresistive material. It is basically a comparison. So we have force sensing materials, force sensing techniques, plantar force detection sensors, and monitoring gate phase. So in piezoresistive sensing, we have conductive forms and conductive fabrics and conductive links as force sensing materials, and they move to the piezoresistive sensing, and then piezoresistive techniques based PSD install system takes place, and then we have the gate monitoring application. And when it comes to piezoelectric sensing, we have materials like metal liquids, piezoelectric ceramics, and piezoelectric polymers, other type of materials used for piezoelectric sensing, and they are used for applications like piezoelectric techniques based PSD install sensor systems. And then we have a stance phase. These are the common materials used like conductive foams or fabrics, carbon-based inks like carbon black, carbon nanotubes, and metal liquids and composite materials combining flexibility and conductivity. So these are the materials which are commonly used under piezoresistive sensors. So this is a tensile performance display. We have an SEM image of the CNT's embedded TPE and a relative resistance curve of the CNT's embedded TPE. And we also have a ringle sandwich structure and resistivity. The plot shown there is a resistivity strain plot which demonstrates the flexibility of the pressure sensor. So piezoresistive sensors are widely used in gait analysis and rehabilitation because due to several reasons. So the first one is monitor plantar pressure during walking or standing, detect gait abnormalities in patients with conditions like stroke, Parkinson's disease, knee osteoarthritis, and provide real-time feedback for retraining movement patterns, and it also helps in be embedded in wearable insoles for continuous monitoring. So here we have a schematic of generalized biopotential measurement where we have a control panel and a lead system where the biosignal acquisition takes place. And we have an external device in transducer where there is an inbuilt audio stimulation, video stimulation, out in triggers. There is a few food switch and an electrical stimulation, and also we have amplifiers and ADC, analog to digital converters. So from there the data goes to the settings where we have a computer and display and for that we have keyboard, mouse, and video and microphone for giving the input to the computer and display. And we have also in network and internet provisions, and we also have printer facilities and also sound facilities for taking the sounds of certain muscle biosignals. And the type of amplifier used here is differential amplifier, and the operation of the differential amplifier is illustrated here besides the schematic. And we have a differential signal input which is amplified and the common signals are attenuated. These are the type of electrodes which are used for EMG acquisition. First one is invasive type and the other one is non-invasive type. As the name itself indicates, invasive type requires needle electrodes and non-invasive type electrodes require surface electrodes. So non-invasive type of electrodes are again divided into three types like dry surface electrode, high density EMG, and textile or flexible printed electrodes. So needle electrodes are one of the earliest and most precise methods for recording EMG signals. They are invasive electrodes that penetrate into the skin and are inserted directly into a muscle to ensure muscle electricity at the level of individual motor units. So needle electrodes are monopolar, concentric, and fine wire electrodes. So these are the advantages and disadvantages of needle electrodes. Next are some of the signal characteristics of the muscle signal acquired using needle electrodes. So the amplitude is higher than surface EMG, and sensitivity records from individual motor units or small groups of fibers, unlike surface EMG which records overall activity. And the frequency range is similar to the surface EMG itself. And the applications include clinical diagnostics, and it also helps in research and for rehabilitation assessment. Next comes the surface electrodes. So the first one, it is AG and AGCL, like gel electrodes. So it is a traditional type of electron. It is most widely used in clinical surface electrodes, and the advantages are high quality signals. They acquire high quality signals and well established clinical standards. And disadvantages include require skin penetration, and there are chances for the gel to dry out, so it limits long-term monitoring and can cause certain kind of skin irritation after prolonged use. And it is also not suitable for daily wearable rehab. So this is the continuation. Like we have next one we have is dry surface electrode. It is made up of conductive metal or polymer pads which are used without gel. They are basically dry as the name itself indicates, and the advantages are quick and simple to apply, which is more comfortable for patients in rehabilitation. And disadvantages include they are more prone to motion artifact and higher impedances, and signal quality may be lower than gel electrode and sensitive to electrode pressure and skin conditions. So here you can see the placement of how dry electrodes are placed. Next, we have high density EMGs. They have grids of dozens or hundreds of small electrodes placed over a muscle. So it can record a spatial distribution of muscle activity, not just a single signal. So advantages are like they have high resolution muscle activity mapping and enables motor unit decomposition. Disadvantages include like they uses like many like dozens of electrodes, hence it is expensive and complex to set up, and it requires advanced software and expertise to interpret, and they are not yet widely used in daily clinical rehabilitation. So the above figure is just a simple illustration of how EMG signal is acquired. The EMG signal is detected from the arm, and the signal preconditioning and transmitting takes place, and where you can see the EMG signal monitoring. And next is the transradial processes based on the Myo wireless myoelectric band. It has a Myo armband which is connected by a Bluetooth, and then for wired we have temperature and force sensors and servo motors and DC motors, and then it goes to a Raspberry Pi for overall controlling. Next, we have the surface EMG and the advancement of surface EMG through last 70 years. So first we have an electrode skin interface, and then it goes to the front end amplifiers and filters where the signals get amplified and the unwanted signals get filtered out, and then it moves to the sampling for digitizing, and it converts the analog signals into digital form, and then it can be transmitted through wire, and wireless transmission also takes place. So this is the continuation, like we have for muscle signals. For acquiring muscle signals, we have textile and flexible printed electrodes. So these are the type of electrodes which is made from conductive fabrics, inks or stretchable materials which are integrated into wearable items, like the wearable clothes we wear, like shirts or sleeves, gloves or insoles. So the advantages are they are more comfortable, they are lightweight and patient friendly, suitable for long term and home based monitoring, washable and reusable, aligns with IoT and wearable healthcare trends. Disadvantages are like they are still under development, durability issues after repeated washing can be happen, and signal quality may vary with movement and fabric tension, and higher production cost as compared to standard electrodes. We move on to the main applications of dual mode control system. So the first one is upper limb rehabilitation robot. Here is the schematic diagram of an upper limb bilateral rehabilitation robot. So the first one is mode self-switching flowchart, and the second one we have ADRC position control block diagram. So mainly it uses two kind of working. First one is feed forward control, which is for early intent detection. It uses EMG for detecting muscle activity, detects intended movement before actual force or motion is seen. Next one is feedback control. It is for confirmation and stabilization. So it uses pressure sensors or force pads confirm actual load or contact. For example, it can be a footstep or grip squeeze. So mode self switching flowchart, it consists of there are two type of exercises. It can be passive exercise or restive exercise, and by switching on to any type, like particularly to any type of exercise, it from after that it is followed by a path generator for generating a path, and then it goes to the position control, and finally to the robot will be doing that particular kind of rehabilitation exercise. And next one we have upper limb robot dual model hybrid self-switching control block diagram. So as I said before, they have a mode switching equation. From there it goes to the forward kinematics or the path generator, and they also have a potential field equation for generating the desired trajectories. And there we have red lines which indicates the desired trajectory. And then we have an ADRC equation at the end for controlling the robot, and we also have a virtual reality vision at the end. So this is an experimental setup and its coordinated control system, and on the other side we have the prototype of the lower extremity exoskeleton and its mechanism diagram. And the third one is a dual mode reconfigurable angle joint parallel rehabilitation mechanism. It has a moving platform and there are four branches, branch 1, 2, 3 and 4, and then we have a static platform which will be fixed at the bottom, and the moving platform will be moving according to the movement given by the foot. And then we have a parallelogram mechanism. So this type of parallel mechanism is often used in balance training platform. Patients practice stability while the platform moves. And then we have gait rehabilitation for the same system to simulate walking conditions, and to seated rehab systems like helping patients recover postural control and core strength. So this is the comparison of the control modes. So when it comes to the complexity, single control mode are simple and they are low cost, while in dual control mode they are more complex and needs fusion algorithms. And coming to the responsiveness, in single control mode they have moderate responsiveness, and for dual control they have high responsiveness, and accuracy is medium for single control, and for dual control it's high, reduces false triggers. In robustness, for single control mode it is weak, and for dual control mode is obviously high or strong. And applications include for single control mode is FES and simple rehab devices and diagnostics, and for dual control mode, as we have just discussed, like exoskeletons, prosthetics and tele rehab. So these are the current challenges in multi-modal rehabilitation systems, like signal quality and reliability, sensor integration and fusion complexity, user variability and comfort, data management and interpretation, cost and accessibility. So these will be the future directions in multimodal rehabilitation system, like advanced signal fusion with AI, personalized and adaptive rehab, cloud and tele-rehabilitation, integration with neuromodulation, standardization and clinical translation. So when it comes to the conclusion, integration of multiple biosignals enhances the rehabilitation systems. We have already discussed. And AI and sensor fusion play a key role in future rehabilitation engineering. And dual control modes overcome limitations of single signal systems in rehab. Wearable electrodes and sensors provide reliable data for grip, balance, and movement. Applications are diverse. Including prosthetics, exoskeletons, gait, and balance training. Enhanced responsiveness, adaptability, and safety result from signal integration in rehab. So these were the references of my seminar presentations. You can go through it if you want. So we have, like, I have around 15 references for my seminar. So yeah, that's it. Thank you.